Okay, yesterday we have discussed design of experiments. Today we will have to do a deep dive on this. Let us do this simple exercise where we'll be looking into interaction effects and main effects. Let us look into the question, how it is framed. For this data, question is we will have to calculate the main effects of factor A and B, and also we need to find the interaction of BC and ABC. BC is 2-level interaction, ABC is 3-level interaction. Let us see how the table comes up. Here it is. To find the effect of A, B, C, BC, ABC, we need to calculate the following. That is, we need to come up with AB. -1 into -1 is +1. AC. -1 into -1 is again +1. BC. -1 into -1 is again +1. ABC. Minus into minus is plus. Plus into minus is minus again. So ABC you'll get -1. So in this way the entire table is populated. That is the logic behind calculating these values. And the response is already provided. So let us calculate each one. Effect of A. How do you calculate effect of A? Effect of A, you see corresponding numbers. All the plus ones, you sum up those values and then you subtract it from all the minus ones. You subtract it from these values. So add all these values, I subtract it from the other values and I divide it by 4. That is a formula that we have already seen. So what is it that we are getting? We are getting 0.5. Response yield increases by 0.5 on an average as factor A changes from low to high values. Low to high means -1 to +1. Low is -1, high is +1. Let us calculate the effect of B on similar lines. So let me erase everything. All the +1s of B you group together. So you add 32 plus 39 plus 27 plus 45. If you see, those values will be here. You subtract those values from all the negative B's. -1, -1, -1, -1. So the corresponding response is 35, 41, 31 and 46. You add all these 4 and then you divide it by 4 to get a value of -2.5. Response yield decreases by 2.5 on an average as factor B changes from low to high. All right. Next thing is, let us look into the interaction of BC. Sum of all +1s minus sum of all -1s divided by the number of positive or negative signs. Always positive or negative signs in our table. It's a balanced design of experiment. We'll have equal number of positive ones and equal number of negative ones. So let us look at this. How are we getting these numbers? 35 plus 39 plus 31 plus 45. Sum of +1s. So let me take you back to the table. We are looking into the interaction effect of BC. Here are the +1s. Plus, 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 plus. So you sum up all the corresponding response values for +1. You subtract it from all the corresponding response values of -1. So that is what is mentioned here. The value you are getting is 1. There is a slight positive interaction between B and C. That is what we indicate, 1. Higher it is, more is the interaction. Interaction between A, B, C. For this, you simply jump to the column which shows ABC interaction. You once again sum up. All right, Anuj. So in order to identify the interaction effect of ABC, we need to refer to this column. Sum up all the corresponding response values against +1 and also sum up all the response values against -1 and then subtract these two. Divide it by 4. Why are we dividing it by 4? Because it's number of +1s or -1s. So number of +1s are 1, 2, 3, 4. Or if you take the -1s, there are 4. 1, 2, 3, 4. Yeah, we sum up number of +1s, subtract it by sum of -1s, divide by number of plus or -1s. So here also we see that there is a slight positive interaction between ABC. This is a positive number, 0.5. So there is a slight positive interaction between A, B and C. All right. How do you create a designed experiment, not an experiment which runs on the fly, but we are going to design an experiment which has to be performed. So for that you need to go to Minitab, go to Stat, DOE, Factorial, Create Factorial Design. Let me go to Minitab and show you the entire thing. So you can use Minitab to create the design. If each factor has only 2 levels, and you can use the default generators or you can specify your own generators. Plackett-Berman design are used for running a reduced number of experiments to study the main effects. This is Plackett-Berman, these are scientists, here that value is. You can also use this, right? And then general full factorial is for designs that have more than 2 levels for each factor. Temperature is a factor. 20 degrees, 40 degrees are 2 levels. If I say 20 degrees, 30 degrees and 40 degrees, there are 3 levels. If I say 10 degrees, 20 degrees, 30 degrees and 40 degrees, there will be 4 levels. So those are the levels and factors. And here in this box, we have to specify the number of factors you have selected for this study. So let me open Minitab. We're just creating, okay? We are not doing anything. We're just seeing how we can create something. Okay, let me go to Stat DOE Factorial. Create Factorial Design. I'm selecting 3. If I select 3, there will be how many? 3. Okay, here, let me open a new worksheet. Okay, Stat DOE Factorial, Create Factorial Design. Number of factors that we are selecting are 3. That is what is first step. Second step is display available designs. Let me maximize this. Okay. So display available design lists the different combinations of factors and the number of runs for a selected design. For example, if there are 4 factors, a full factorial design would need 16 runs. Yeah, look at this. If I have 4 factors, if it's full, then I'll have 16 runs. A 4-factor experiment with 8 runs is a resolution 4 design. Here it is. So what does that mean? we will discuss in detail. So first of all, let us try to understand this, and then I'll show you the same thing in Minitab as well. So we have green color and yellow and red color in this display available designs. Green colored designs are safer to run as they are resolution 5 or greater. See, if you say resolution 5, 6, 7 and greater, 8 and greater will always have a green sign. These yellow colored designs are the next best. They're resolution 4. And the last thing is red. Red design should be avoided unless you are sure there are no two-factor interactions. If you feel that temperature and humidity, right, for instance, is not impacting your AC room temperature, and if you're 100% sure, only then you can go with resolution 3. Yeah, this chart mainly is for your understanding only, right? Nothing can be selected here. It just tells you how many runs are needed for the number of factors that you're selecting. So this is what it is. Yeah, if I have two factors, then I need 4 runs, full runs. For 3, I'll have 8 runs if I want to run full factorial. But there is also 3 resolution, which is possible. In that way, you can, look at this. Wherever there is green color, that is a good thing. Wherever there is yellow color, that is the next best thing. And red color is, try to avoid it as far as possible. All right. We are just trying to understand everything, the options. That's it as of now. Next thing is select the appropriate design. In this case, there are 2 options, half factorial and full factorial. Indicate if there are any center points in the design to check for the curvature. What is a center point? I've told that if one of the factor is temperature, then if you're having the temperature as 0 degrees, which is low, and 40 degrees as high, then you are having only 2 points. Instead of, if I bring in 20 degrees, then I'm bringing in a center point. Yeah, that will actually help me identify the curvature as well. Suppose this is 0 degrees. Yeah. And this is 40 degrees. Okay, if I join these two, it will be a straight line. But if I include 20 degrees, then there will be a curvature. Graph will look like this. Okay. Indicate if the designs are replicated to estimate error in the results and model significance. It also indicates if there are blocks in the design. What do you mean by blocks? If I'm running experiment 1, 3, 5, 7 as one group, that would be called as one block. If I'm running 2, 4, 6, 8 as another group, it will be called as second block. Block is nothing but group of tests that are run together. Alright, so let me show you this in Minitab. We are just exploring the various options, that's it. So number of blocks, you can have 1 block, 2, 4. right? Number of replicates 1 to 10, and number of center blocks 0 to 25, etc. And you have half factorial and full factorial. What is the next option? Next option is entering the factors. You can run the design in either coded or uncoded space. What do you mean by coded and uncoded space? In coded space, low settings are denoted by -1 and high settings are denoted by +1. You have done some coding kind of, right? In the uncoded space, we use the actual values. For example, we have used actual values here. Speed. If you are traveling at 10 kilometers per hour, it is low. If you're traveling at 100 kilometers per hour, it is high. And on similar lines, they have given quality and service as well. Let us enter these names and values in Minitab now. So here I'm clicking on factors. These values I've already entered, hence they are appearing. For you, these values will not appear. It will be blank. You'll have to enter all these details. Speed is numeric. I'm telling 10 is low and 100 is high. Quality also I'm selecting numeric, or you can select text. High quality, low quality, you can just enter in that way also. For that you need to select text. Yeah, but we are selecting numeric in our case. If I use -1 and 1, it is called as coded. If I use the actual numbers, it's called as uncoded. So I'm entering the actual numbers. Then we have service, which is text. I'm entering poor service and great service as two extremes, low and high. Let us see what other options are missing here. Okay. Last thing is you'll have to select on, click on options and then fill in the details. Either you can fold the design, which is a useful way to improve resolution of your fractional factorial design. And one more thing is you should always randomize the runs to ensure that any unknown noise factors do not affect your study. If you have people entering your restaurant in this order 1, 2, 3, 4, 5, 6, so on and so forth, as in how each person enters, you select, you decide on what is the service that you have to provide to them, and at the end you collect the customer satisfaction. If you do it in this order, what happened, Anush? Now there is a slight lag, I believe. Yes, yes, you'll have to. Okay, let us do this in Minitab once. So I'm randomizing the runs. We can fold or we can unfold the design. I'm clicking on OK. What did we just do? We have created a design. This is what we have created now. This is the design that we have created. We are doing experiments on what is the best solution. Alright, let us understand the table that got generated now. Here is a standard order and here is a run order. What is the difference between these two? You need to conduct the experiments in this order, run order. Conduct this first experiment with speed 10 kilometers per hour, quality is 99, and poor service. And then you'll have to do second experiment, third experiment, fourth, so on and so forth. So this run order is the order in which you have to perform the experiments. Yes, we have generated the table. Yes, exactly. We generated the table in the order that we want, with the factors that we want. Yeah, but how to perform my experiment? What should I do? This table is going to tell me. All right. And this is a standard order. Standard order is the order in which Minitab creates a design. If these two columns are not the same, that means you have randomized your runs. Yeah, you have randomized the runs. And look at this value, there is a center point. What do you mean by center point is equal to 1? Center point is equal to 1 implies there are no center points. If there were center points in the model, they would be indicated by a 0 in this row. And you know what is a center point. If I have two extreme values, speed 10 and 100, suppose, these are the two extreme values that I have, low and high. If I include speed as 50 or 40 or 30 or some other numbers, then there would be a center point. In such cases, a column would have shown 0 instead of 1. Next thing is blocks. All the tests have the same block number 1. So they are run together as one group. If there were blocks, some tests would have 1 while others would have 2. Right? Some other would have 2, 2, 2, etc. Number 2. That means all those which have number 2, you would have run it as one experiment. All the places where you have 1, you would have run it as second experiment. Yeah. Number of test runs required. If there are no center points, no replicates and no blocks, the number of runs is given by 2 raised to the power k. So in our case, we have 2 raised to the power 3, which is 8 runs. In the table that we have seen, we have 8 runs. 1, 2, 3, 4, 5, 6, 7, 8. Create the design for 3 factor, 1 center point, no replicates for corner points and no blocks. There is only 1 center point, 3 factors. For 3 factors, we know that number of runs is 2 raised to the power 3. And you are adding 1 center point, which is plus 1. So the number of runs is 9. Create the design for 3 factors. Whenever there are 3 factors, it's 2 raised to the power 3. We know that. There are no center points. There are 2 replicates for corner points. If there are 2 replicates, then you just multiply it by 2, you'll get 16 runs. This is just mathematical calculation, that's it. Yeah. So let me ask you a question here. Create a design for 4 factors, no center points, or okay, let me put it here. Create a design for 4 factors, 2 center points, and 4 replicates. Janusz, can you tell me how many runs you would have? 2 raised to the power 4. Okay. Multiplied by 4. That's fine. That's it. I also told that there are 2 center points. Have you accommodated 2 center points? Look at the second one. Look at the second one and then let me know. What will you do with the center point? This one. You can read this. Yeah. In this case, we have 1 center point. But I told if there are 2 center points, what would you do? If there is 1 center point, I'm adding 1. If there are 2 center points, you'll add how much? 2. That's it. Simple. Yeah, exactly. So to your solution, you can just add plus 2 to make it complete. All right. Power and sample. Determine the number of replicates required if we have a 3-factor full factorial designed experiment with a power of 90%. We are interested in detecting a difference of 1 and the standard deviation of the output is 0.5. We'll just have to do this. We have 3 factors. It is a full factorial, so we'll have 8 corner points. Number of corner points when we have 3 factors is 2 raised to the power 3. If it is full factorial, you'll get 8 corner points. So let us do this in Minitab. We just want to know the number of replicates. That's it. How many times I have to repeat the experiment because it's full. Yes. It's a full factorial. If you have 3 factors in full factorial, here we have 3 factors. For example, speed, quality, service. Whenever you have 3, you'll have 8 runs. Yeah. 2 raised to the power 3, yes. 2 multiplied by 2 multiplied by 2, yes. Okay. So let us go to stat, power and sample size, and then 2-level factorial design, right? If I'm not mistaken. Yes, 2-level factorial design. So we have 3 factors, 8 corner points. What do they want to check? They want to check whether the difference is 1 with power 90% and standard deviation 0.5. So power 90% is 0.9. I have put here. Standard deviation is 0.5. I mentioned it here. I just click on OK. This is telling that you will have to run the experiment twice. Number of replications should be twice. All right. Let me know when you want to stop. Until then, I'll just continue. Blocking. Blocking means grouping together few of the experiments. All right. If there are 3 factors and if I do not have any center points, no replicates, and if I have 2 blocks, if I have 2 blocks, 3 factors, then it will be number of runs will be 2 raised to the power 3, which is equal to 8 runs. No tests are added, additional tests, right? Just because I'm telling there are 2 blocks doesn't mean the number of tests are going to increase. No. No tests are added. But some tests are run as block 1. Probably you have 1, 3, 5, 7. Maybe these 4 are run as block 1 experiment. And 2, 4, 8, 10 maybe. Maybe these are run as 6, 8 are run as another block. The blocks are selected in such a way that they equally influence the results of all the corner points. So when I say corner point, suppose this is a die. Sorry, my bad. Suppose this is a die, then these are the corner points. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 corner points. Right? So you have to select the blocks in such a way that they equally influence the results of all corner points. You have to select in such a way that all the corner points are selected. It is as simple as saying that each block should have equal number of runs, and you have to include all the runs in the blocks. If I have 1 to 8 runs, I cannot say that 1 to 4 will be block 1 and then 5 to 7 will be block 2. Why? You cannot say so because here you are including 4 runs, here you are including only 3 runs. And what will happen to the 1 run that is left out? Alright. Hence the effects of the block on the main effects is minimized. So I'm just going to stop here, Anuj.